Hello again, everybody. Welcome back to another episode of the Flocode podcast. I'm your host, James O'Reilly. Today I'm doing a little video introduction to my guest, Ramaseshan Kannan. We just jumped straight into chatting when we had our podcast episode, so I didn't have time to introduce him on the podcast, so I'll do so now. He is the Head of Computational Science at Arup and a Royal Academy of Engineering Industrial Fellow. He's got a PhD in Numerical Linear Algebra from the University of Manchester and a very interesting career that spans both industry and academia and software development. He's been at the forefront of research in the civil and structural engineering industry for many years now as it relates to computational science, machine learning, and numerical analysis. This area of research and work is of deep personal interest to me, and it was really fun chatting with Ramaseshan about a lot of this stuff. And while he digs into the underlying theory and mechanics and the creation of these tools, I feel like myself and many others are on the other side of the fence here, trying to figure out what are the most practical ways that we can implement these tools into our projects and for our clients. It's tough because a lot of these ideas and numerical concepts they take time to learn and to understand, and everything has both an opportunity and a learning cost associated, and sometimes you don't know what the cost is until it's too late, and then you realize, man, what was I thinking? Why did I do that? It's of no use to me. But such is the art of progress. I had a blast talking to Ramaseshan. He's a very cool guy, and he is a clear thinker and just a fun person to talk to about a lot of these topics. So I hope that everybody out there enjoys this episode as much as I did, and we got lots more news in the pipeline. I want to thank everybody for all of the support for the Flocode project. I'm having a blast doing this. It's ridiculous that it's still ongoing, and what more can I say? I'll see you guys in the next one, and now on with the episode. All the best. Bye-bye. Hello, everybody, and welcome back to another episode of the Flocode Engineering Insights podcast. I'm your host, James O'Reilly, and today we have a very interesting guest, Mr. Ramaseshan Kannan from Arup. Ramaseshan is the Head of Computational Science at Arup, and I hope this is going to be the first of a few different chats that we have on some really interesting stuff in our field. So Ramaseshan, thank you so much for coming on board, and you're most welcome to the Flocode podcast.
Thanks, James. Thanks for having me. Thanks for the kind invite.
So, as I always do, the first big question is, what is your life philosophy in a nutshell?
Yeah, start with the really nice, simple ones. um, I guess in the most part, I would say I'm led by what I'm thinking um, at any given point in time, in the sense that I like to evolve it organically. But I guess there are a few underlying principles I like to kind of keep coming back to. And again, both at a conscious as well as a subconscious level. Um, I suppose one of them is a desire to have an impact, a positive impact, an impact in the sense of impact through our work, my work, in being able to leave the planet in not too worse a state than how we found it when we arrived. There's that kind of underlying theme, and that's kind of dictated some of what I've done or some of the decisions I made. The other one is probably boredom avoidance, right? How do we find work which is at the intersection of useful and societally relevant, but also reasonably intellectually stimulating?
An impossible balance almost.
Yes, yeah. That it's it is that kind of in your obligatory Venn diagram, that is a small wedge of intersection. Yes, you're absolutely right.
That's brilliant. That's brilliant and insightful too. So, give us some context. Where did Ramaseshan begin his engineering journey? How did you end up where you are? Just kind of give us a rundown of your engineering history.
Yeah, so I studied civil engineering in my undergrad and masters. This was at IIT Madras back in India, Chennai. And I think right from the start, so it was like a 5 year program. You major in civil engineering and a master's in kind of a specialism. So in my case, that was infrastructural civil engineering. And right from the start, especially this was probably after I took my 101 sort of structural analysis course, I thought I was more interested in creating the tools rather than using the tools. I have this kind of vivid memory of sitting in one of those lectures, and the first time our structural analysis professor was talking about bending moment diagrams, and he then said one of the things we were kind of discussing was, how do you get the bending moment at this point to get to zero? What can we modify in this structure to? And then he put a hinge there, and that kind of blew my mind. I thought, how can you get a computer to kind of work that out? Anyway, so yeah, it kind of I was interested in the programming side of things, and then that led on to when I graduated. Arup was advertising the role developing structural analysis software. So we have
What? Sorry, Ramaseshan. What languages did you begin with? Was this like MATLAB or C++, or what did you start with back in university? What were they talking about?
I was exposed to C++ fairly early on, and that's what I stuck with. And
Horrible.
in fact, MATLAB came a little later for me when I was doing my PhD research, weirdly enough. But yeah, I was, and I think that's also, so if I had done my kind of engineering degree today, that might have well been Python. But I think C++ has been kind of around for that much longer. But it also has its own sort of learning curve, and we can get into all of that a little later. But anyway, so yeah, it was C++ I was initially exposed to, and really enjoyed it actually. Really enjoyed just learning the language for the language's sake. I mean, the various quirks and sort of idiosyncrasies as any language would have, and C++ has a fair share of its own. So really enjoyed discovering those. Yeah, so as I was graduating, Arup was advertising this role, developing OSS GSA, which is Arup's commercial structural finite element software. And this was a role back in India. So I started there and then started developing tools in GSA for things like steel design checks, steel design automation. How do you do buckling checks, for example, or how do you take, let's say, a BIM model, and this was the early days of Revit. This was kind of 2005, right? So Revit was just out. So how do you take a Revit model and sort of convert it into a structural analysis model in GSA and so forth? So working on some of those kind of workflow type tools in and around structural analysis. And then eventually I became quite interested in the solver side of things, basically what goes on under the hood once you press that analyze button. And then that led me on to proposing that I go do a PhD to improve the solvers that we have within GSA, to overhaul some of them and sort of bring them up to speed with the latest state of the art, but also kind of develop new techniques to solve problems fast, more efficiently or more accurately and so forth. And to my surprise, my managers agreed to fund the PhD. So that landed me in University of Manchester in the maths department, where I was looking at eigenvalue problems, developing new linear algebra solvers to kind of put into GSA. And that was quite a satisfying experience, because a lot of the times when you do a PhD, you are struggling to discover the problem. A lot of PhD students, spend a lot of time trying to figure out what problem to solve. Whereas in my case, there were already a set of ready problems waiting to go, right?
Well,
One after the other.
what's interesting about that is, a lot of PhD candidates go directly in after their undergraduate, and
Yeah,
the advantage of having a few years experience in the industry and then going back is huge, and it kind of contextualizes those problems for you. So you're like, you actually understand, okay, why do we need to solve this, and how much time is this going to save, and how much more elegant is this going to make the software, or this is a great avenue for improvement. But you have all of that context. Did you find that yourself when you went back to your PhD?
yeah, absolutely. Yeah, all of those things you said. What's the in more modern terms, we would say, what is the business value of doing this? But even from a research perspective, where do we see this technique ending up as? What is the impact you could have through this research? And so, yeah, you are better placed to answer some of those questions. And in that sense, you have there is also an intrinsic motivation because you can connect yourself to that impact. You see how, or at least you have some projection of what impact it could deliver. You then kind of propel to explore certain directions. So yeah, that's also interesting. Yeah, so that PhD led on to a couple of new solvers and a new piece of tool that used a bit of machine learning to understand where engineers make errors in their finite element models, which is now one of the more widely used tools within GSA. And so after the PhD, I returned to Arup, and since then I've been leading various solver-related analysis capability-related initiatives, starting from a rewrite of various portions of the solver, leading on to building a team that kind of solved a wider range of problems, not just structural but also geotechnical and so forth. And then more recently, onto um, basically research and innovation within computational science as a broader area. Yeah, so here we are.
That's a very interesting and niche path that you've taken in our industry. There's not many people that kind of fit into that same flow. Um, and I find it interesting that you went directly from university into software development from a structural engineering degree. Like, that is rare, and especially with I find C++ to be challenging, to say the least. Um, so
Yeah, so just on that note, I think and I think that is, you're absolutely right. And I think if I were to enter programming today, I would probably pick a different route. Not least because the level of maturity and the tool sets and the everything else around the ecosystem of developing software, it has evolved so much in the last sort of 20 years or so, and it's really kind of great to see how it has evolved. That the barrier to entry has been lowered, and I think it should be that way. I.e., you want that barrier to entry to be as low as possible, so that more engineers can code, more engineers can use automation and so forth. Yeah.
so in your opinion, for young engineers out there, or even practicing engineers, how do you think that they should think about approaching code? There's a lot of reservation out there. There's a lot of people that are overwhelmed, don't know where to start, etc. What are your thoughts?
Um, and I think this applies equally to myself and my own team, where we are constantly. So it's not just one single problem we're solving and one single piece of technology we use. We're constantly having to pick new ones. And so, in some ways, a similar set of questions apply even to our own day-to-day work. And I think the only thing I've found effective is, get stuck in some, just jump straight into the
Yeah.
deep end. You pick a problem that you want to solve, and then it's sometimes helpful to have like a starting point. So, for example, you start with a piece of code someone has already written, and you want to identify a bug in it, or you want to improve a certain feature in it, and then you kind of work your way downwards from that. When you start, you have quite a high level view of, you have a piece of code in front of you, and then you start digging further, and you kind of peel the layers of the onion, as it were. And in the process of that peeling, you discover and you learn, and learning has become more easier than ever before with ChatGPT. There's no excuse at all to not use it when you're writing any new piece of code. So yeah, that would be that's been my kind of go-to tool. That's been my tried and tested way.
It really is. It's really interesting, to see where this is headed, because in the last couple of years, just the quality of the responses that are coming from tools like ChatGPT for writing code has dramatically improved. And I wonder if the curve is flattening now, where we're not going to see such big leaps in terms of, its ability to comprehend things and, give us more complex outputs. But if the future of technology is anything like the past of technology, things are going to keep improving. And, where are we going to be in 10 years with these tools? Like, what do you think?
I think it's hard to say. I mean, language models themselves, as you were saying, we are discovering newer capabilities every day. People are talking about whether they can reason or not, and so on and so forth. There is all of that side to it, and there is, how much new data we're going to have to train language models in their current form. But there are potentially other avenues we haven't yet explored, using the same set of underlying techniques. So, for instance, you could sort of conceive. I mean, at the moment, the way a language model works is it sort of learns these symbols and how the symbols kind of occur together, and it learns distributions over them, and then the text it spits out is based on the distributions it's learned. But that doesn't have to be restricted to symbols from natural language. It can be, you could evolve a language of your own, for example, for 3D objects, right? So we constantly deal with things like buildings and tunnels and bridges and whatnot, and they're all 3D data. But 3D data represented in real world coordinates. But what if we had a language to actually, so finite set of symbols on which we build this 3D data, and if we come up with that kind of language, you could then presumably use that as a basis for discovering or feeding it to a language model type technique, which can then generatively produce newer forms of that language, i.e., 3D models. And so, yeah, I think it's hard to say where it's going. Yeah,
That is, I never even considered that, and that is such an interesting idea. Is this just an idea that you had, or is there some research on this?
there's been some research in some of these directions. I don't know if its uses. So conceptually, yes, it has been looked at, I believe, but whether or not it is using a similar approach to what I had in mind, I don't know. I haven't read the papers yet.
That's a fascinating idea, and you see some tools out there now, like I think ANSYS and Altair have some interesting physics AI models where they're they're kind of not quite what you just described, but impressive capabilities, able to iterate through like a broad variety of different shapes and give you stress patterns based on sort of, 50 different, slightly different geometries, and give you quite impressive results. That's very cool, but that's almost, what you're talking about, like creating a new language almost to map the 3D world into some sort of an LLM that's specifically trained for that task. That is such a interesting idea, and I wouldn't even know where to begin of how the architecture of how something like that would work. But that's very cool.
Yeah, it's not one I've kind of had a lot of time to uh, think through in great detail. But yeah, it is one of these sort of pipe dreams. But your other point about the likes of um, ANSYS and so forth, exploring physics-based AI, yes, that is something we have indeed kind of looked at and explored. And I think the key thrust there is whether you can use machine learning based surrogates to be able to let's say you have a design space that's controlled by a set of parameters. Let's say you have a tall building, you have a core, like a concrete core, and then the deflection of the tall building right at the top of the structure is determined by the amount of wind loading as well as thickness of core and so forth. So in the early stages of the project, you are trying to understand, well, how do you want to size your cores with respect to the overall dimensions of the building and so forth. And this is a kind of problem that is kind of, you could find it across various disciplines in the built environment. And quite often, you answer these questions in the early stages, you're answering them using rules of thumb or heuristics. But what if you can actually bring the full power of what we know through simulations, so things like finite element analysis, into those earlier stages uh, where the your ability to control the cost and the overall shape of your structure and the embodied carbon and so on and so forth. That is the greatest in those early stages. So, what if you can bring that high fidelity information in the early stage? So, we have been exploring the use of machine learning based surrogates, which can be trained by generating lots of different variations of geometry, as he was saying, of a given sort of building or a given sort of base geometry, and from there interpolate between those spaces. So you can, your parameters, whereas previously you could have explored just a few design configurations from those parameters, now you can explore a vastly higher number of design configurations and be able to answer questions about those configurations almost in real time. So yeah, that bit is very much kind of, it's a bit more tangible, let's say.
So I want to talk about this a little bit more because this is kind of your field here. We're talking about, structural analysis and design is one thing, but you're talking about a much larger global view of almost all aspects of a project. So, as you mentioned, the embodied carbon, the sustainability of a project, the life cycle of a project, all of the different aspects that make up a project, all stakeholders, everything. So, let's zoom back out. And you had mentioned before we started the call defining the difference between computational design and computational science. So
Mm.
I think it would be good to give listeners just a kind of a broader sense of what it is that you do currently at Arup and the definition in between those two terms.
Cool. Okay. So um, my title is Head of Computational Science, and it's a discipline that has evolved through, and others have also called it computational science and engineering. So it's a discipline that has evolved through the physical sciences and through the mathematics communities within academia. But actually, in reality, the remit of this discipline covers something that we've been doing for decades within engineering, which is basically the underlying numerical analysis, the underlying mathematics behind a lot of analysis we do, whether it be doing a CFD to understand pedestrian wind comfort around an urban neighborhood, or to understand how a building will behave in an earthquake, or the flow of water through a river catchment, hydraulics, and so forth. So the underpinning mathematical models that sit underneath all these engineering problems, uh, they, um, they share a common family of a common vocabulary of understanding these problems, and that is what we kind of mean by computational science. So it's sort of the intersection of applied mathematics, engineering, and computer science, because ultimately we are solving these problems computationally on a physical hardware. Um, and that's, as a discipline, it has existed within engineering for decades, but we haven't necessarily called it that. But more recently, what we have seen is a realization that we can take techniques that we are using in one subdiscipline, let's say structural analysis, and that can be used quite directly in several of the disciplines. Or you sort of make the maths a bit more abstract and you take something like, I don't know, a probabilistic approach like Bayesian inference, and that can also translate from one kind of problem domain to another problem domain. And so the whole idea behind recognizing the role of computation science within the built environment is for us to be able to, apply a common set of capabilities and knowledge across a range of emerging and new challenges that we are seeing in built environment. So that's computation science, and I think one thing I must mention is the big shift we've seen that has prompted us to kind of think in these directions is over the last sort of 5-10 years or whatever, data has come to the party. And so we are having to kind of evaluate. It's not just models, predictive models that we've used for design over the decades that we need to think about. It's also, how these predictive models interact with the data that's coming from the real world. And so we are seeing a convergence of families of techniques from various disciplines, each kind of building on, standing on shoulders of giants and building on each other's strengths. Computational design, on the other side, is kind of the way I see it is the application of some of these methodological aspects in day-to-day workflows and tools and deliverables. And so it is what I see the vast majority of practitioners, people who are kind of working on projects, it is going to be the set of techniques they're going to be using, a set of tools they're going to be using, with the intent of kind of providing a design for a certain purpose, and computational science being the sort of the methodological aspects that underpin those activities.
That's that's an excellent overview of the situation, and I've been working now in the industry for maybe about 14 years, and it's amazing to me how these different layers of how data is being incorporated into design decisions, and how clients more and more are asking for more clarity on risk. They're asking for more clarity on cost of things. And like you said, using stuff like the Bayesian method or different statistical methods to sort of tie the real world into what people have been doing for generations in finance and in other sectors. But the way you put it was perfect, because it's basically a family of techniques from multiple different disciplines, but they're all transferable and they're all relevant. And you see the same thing, whether it's like in CFD or in structural analysis for finite element stuff, and also in like finance. These statistics help so much in making decisions, and that's what we're in the business of, making decisions, really. So I think you nailed it. And you mentioned some of the power of machine learning applications in what you guys are currently looking at. Where do you see the biggest hurdles or the bottlenecks in terms of gathering all this data? Like, everyone has tons of data, but how do you decide what's useful, or how do you manage this data? What would you tell, let's say you get a chance to talk to Transport Scotland about, they've got a fleet of bridges. What would you tell them about data collection and how it could be useful for them?
Yeah, I think so. I'd like to answer that, but also perhaps step back for a moment, maybe a little later, and then also discuss challenges we have around some of these data conversations from a business perspective, i.e., where is how can we motivate the right business case, the right business model for someone like Transport Scotland to go ahead and actually invest in collecting the data and then invest in the infrastructure to actually do something with the data. I think those are two separate challenges. Both will need to be answered. Um, so I think to your question directly, I think the I suppose my pitch then would be, tell us your pain points in terms of looking after your bridges, looking after your assets. What are the risks? What can you quantify, for example, the losses when you have to close two lanes over the fourth crossing because you suspect a certain element, a certain member has exceeded a certain state of damage that they shouldn't be in. And so what are they? So tell us, what risks you anticipate in operating your infrastructure, and what your pain points are, and we work backwards from there and to see how we might be able to address those. And in answering some of those questions, we might be able to see, for example, that you instrument certain bridges with certain kinds of sensors. You can then fuse it with either what we know about the physics of these bridges, or indeed fuse it with what's going on elsewhere on the bridge. For example, understand what traffic is going on them, passing through them, or what the temperature variations are across the various seasons. And from there, work backwards to say, well, can we predict in advance if a certain member is going to need, or a certain part of the bridge is going to need any work, any maintenance, any downtime, and how do we mitigate the risk around carrying out those works. So those would be the kind of arguments we'd have to, that would be the story we'd want to weave to be able to motivate investing in data.
Well, the point that you brought up initially is so important, and all of the engineering methods are fascinating and interesting, etc. However, it's the business case that drives everything, and you have to convince owners or managers to part with cash to fund specific engineering objectives. So I'm sure that's probably an interesting part of your role. Is there are many rabbit holes. How do you decide what rabbit hole might be worth going down?
Yeah, yeah, it's what keeps me up at night. Really, I think. So connecting back to what I said right at the start, be at the intersection of the interesting and the useful, and I think discovering the useful part of the Venn diagram, because the interesting bits are kind of, they come thick and fast. Ideas are dime a dozen, right? You can explore any number of ideas, and we're not sitting within Arup. At least we're not like we're not a research institute, although Arup is quite kind of progressive in how it thinks about investing in research and so forth. But despite that, we're not an academic institute. Uh, yes, the business benefits definitely need quite a lot of thought, and I think the way we kind of tend to think about it is effectively what I think of as a working backwards methodology, where we define a set of very high level goals and we work backwards from there. So let's say decarbonization, resilience are two very high level goals. We work backwards from there and say, well, what sort of outcomes do we want to see that can meet those goals? So things like, I don't know, be able to deliver designs with reduced imported carbon, or be able to maintain our existing assets so that we don't have to demolish and rebuild, yada yada. And from those outcomes, we then work backwards to see, well, what sort of digital solutions we might be able to create that can sort of target those outcomes.
Yeah.
And then what research do we need to put in place today to be able to deliver those solutions tomorrow? So that's kind of the trail of thought. But then, so that's working backwards. And then you can then work forwards from there to say, well, we've developed this piece of prototype, and then we want to apply it to this project. We just pilot it on this project. And then based on the kind of the success or the failure of that pilot, we then decide we want to build on this further, we want to pivot and go do something else. And quite often it tends to be a mix of the two, i.e., you don't, because this is research, you have to be open to kind of your outcome, or rather the outcome of that exercise being at anywhere in that spectrum. But what you are aiming for is to be able to come up with a set of reusable tools and techniques that can then be applied to an adjacent problem. And that is precisely what we're seeing as we go through this journey. I don't know if that answers the question, a bit of ramble.
No, it did. It's a difficult question to nail down, and you bring up an interesting point, and that is like the design of tools for reuse. And whenever I have an engineering problem, I always start, writing code with the intent of like, I'm going to write this in a really nice, well documented way that I am going to use this again, and I can parcel this up to somebody and they can use it again. And I imagine this big long chain of usage of whatever tool it is that I'm creating. But the reality is that almost every time I sit down to design or do something, I'm building stuff from scratch, or it's slightly different, or I have a better way of doing it. So you're always juggling, do I need to optimize this to the nth degree, or is the perfect level of simplicity is it's good enough to do what it needs to do, and then you move on.
Especially, and I think that's where there is a subtle difference between the kind of role I have and the part of organization I sit within versus someone who might be a practicing engineer on a project, for example. And I have a huge amount of admiration for those who have a day job of delivering these designs on a project to a paying client and are yet able to develop software on the side to be able to deliver it. Because it's one thing for someone to do it as part of their daily kind of, it's what they do, but those who can kind of do both, they're very good at juggling the two and then being able to strike the right balance. So yeah, I'm a fan. I'm an admirer of anyone who does it.
Yeah, it's there's a lot of pitfalls to be had, and that kind of brings me on to another section. So you have a lot of experience with solvers, and I'm interested to just hear broadly your opinion on commercial finite element solvers. We don't have to get into any specifics of any particular softwares, but just broadly speaking, what are your thoughts on how structural analysis programs are handling solvers? Will we see much in terms of evolution over the coming years? As we mentioned earlier, AI is becoming becoming more of a factor. And then the second part is the risks in numerical computation. So what are your thoughts on that? Solvers and then the risks, Ramaseshan.
How long have you got?
Yeah, this episode will be 1 week long.
I think solver wise, I think there's a lot to be said. Within the civil engineering market specifically, we've seen an evolution over the ages, both in terms of the problems that solvers tackle. One of my colleagues, whom I worked with for a long time, he's been developing solvers for nearly 30, 40 years. And he tells us that when he started dynamic analysis wasn't something that people used to do quite commonly. And there were basically rules of thumb to approximate things like the period of the building. And you would still see that to this date in places like the ASE code.
And you know what, Ramaseshan, is that stuff is still very close to the truth.
Yes, yeah. I think what where it can be different is when you have structures for which those rules of thumb weren't necessarily thought about.
Yeah.
And again, we can get into this. There's some research that we've done that has focused on exactly that aspect of heuristics and rules of thumb approaches. So anyway, so it's evolved from those times where we had where we've kind of seen a shift in terms of the modeling fidelity, modeling accuracy, going from 1970s and 80s up until what we have today, both in terms of the underlying techniques that solvers use, going from linear static analysis up until nonlinear dynamic time history, and so forth. And then there's an evolution in terms of the problems that we solve for the end user. So again, it used to be that a model with 100 elements used to be a large model back in the day, and now it is you could be in millions of elements and still be able to solve it on a reasonable sized desktop. So those are the two kinds of evolution. So in terms of the performance and in terms of the accuracy and modeling fidelity, and that then allows us greater insight into the behavior of the system that we are trying to design for. And that means you can have better estimates of the forces and the responses, so the capacities and the demands of the system, and that allows you to be better, more efficient with your use of materials or safer, and all of that has evolved. So there is undoubtedly kind of a positive evolution in that direction. What we are not seeing so much of is an increase in the level of transparency or the level of kind of analysis, being able to query the results or where things are coming from. So we've seen a shift towards almost like a black box, an increase in the black box style behavior in certain parts of the kind of simulation market, let's say. And so something that we are quite conscious about, and this is, my team and I, we constantly kind of argue about it and spend hours discussing it, is, how can we produce analysis that is not just allowing the engineer to be efficient and productive, but also gives them a transparent view of what their analysis is doing so that they can query the result, they can understand system behavior, they know where these results are coming from, nothing behind the scenes. And I think that is, it's something that you have to consciously do as a software team. It's not something that will happen automatically, right? So that is one area of work, or rather one area of thrust, if you will. The other one that I'd like to kind of emphasize is a lot of what we've been doing in how we use these analysis software. So again, across disciplines, so it could be structural, geotechnical, and wider, is we use them for design of a given asset, right? So you're designing a bridge or a building and so forth. And a lot of it is sort of new build and all of that. But as we move forward, there are two other things you need to do. You need to sort of be able to understand how you look after existing assets, and therefore understand how you want to prognose their life and so forth. And in so doing, you have to look at techniques like being able to solve inverse problems. So if you have some data about how an asset is performing, do you want to be able to calibrate a finite element model so that its behavior reflects what you see in real life? So when you move toward those kinds of paradigms, you're not looking at single solutions, but actually multiple solutions. So you're looking at probabilistic answers. And so we are sort of almost paving the path to a place where you're running these solvers inside an outer loop where you're solving those those bigger picture questions. And so you're running these solvers, instead of running them a handful of times for designs that we've previously done. We are having to run these solvers, I don't know, thousands of times or hundreds of thousands of times. And so what changes that does that need to kind of what changes do we need to bring into how we develop these solvers and the sort of software that sits around the solvers to be able to operate in those kinds of paradigms. So those are some of the kind of areas where I see kind of emerging directions.
Yeah, there's a lot of stuff that you just said there that was really interesting. And the first point was about that tightrope. You know, you have a commercial piece of software. How open can you be? How much sort of commercial competitive advantage do you want to retain by keeping proprietary pieces of that code proprietary? For me personally, I've run into that problem often with, I've some sort of complex model and I can't quite figure out exactly what's happening at a specific place. And I'm like, what the hell's going on? I try to call up the support. It's difficult to get a hold of the right person. Either I can't explain the problem correctly or they can't interpret the problem correctly, but I end up just banging my head off the wall and then come back and make some sort of a conservative assumption and move on. And that's the reality of design. I don't know how to balance that with, obviously it'd be great if everything was open source, but you need to make money, and there's, as you said, there's risks. But the other point that you touched on that is very interesting is you mentioned the evolution of these solving tools and how they began with quite simplistic models, and now we have models with millions of elements, sports stadiums or whatever, giant systems. And as you also mentioned, the evolution of that, now we have these complex structural systems, but now we start adding in a temporal factor and the decay of the concrete over the lifetime of the structure, or how much CO2 was created with this particular volume and grade of concrete during construction. You're talking about starting to merge all of these extra aspects of our field into these models. Essentially what you're saying is just going to keep getting bigger and more powerful and more robust.
Yeah. So again, it connects back to what we were discussing earlier about computational science and how this is changing as data has come on the scene. And really, this is, so when traditionally when we've done design, we've created models, and these models are underpinned by our knowledge of the physics of the system, and then we use that physics to predict, simulate and predict, and based on those predictions, we then design, because we say the prediction is for the capacity, and then this is going to be the response. And I think the way that will need to change possibly is for that physics to be able to incorporate what's happening in the real world, because so far that physics has been sitting in isolation. It has been sitting in an idealized setting, and the way we get around that idealization is, firstly we stick to things like linear elastic behavior, right? So we seldom go beyond linear elastic, and sort of that's partly a consequence of the idealizations we're making. So that is one way the physics will have to sort of grow, but also it'll have to grow to be able to assimilate what's happening with this asset in real life, because it's not just the physics of a newly designed structure that you're going to have to grapple with. It's also something that already exists in real life, and be able to do that with a reasonable level of accuracy, right? So you can't, if you only stick with really small strain behavior, for example, you're going to miss out on what happens when the structure is really, or the system is really pushed beyond those limits.
Yeah, exactly. And they're the things that you need to worry about, as a design engineer. You'd mentioned something there about idealization, and that's something that is always a challenge. You have these different statistical methods and you have these different numerical methods, but all models are based on assumptions that you make. It's like you have the
Yeah.
inputs and the outputs, but like, what do you put into the input? You have to figure out how to idealize the real world, as you said, and you
Mm.
have these amazing tools, but how do you idealize some of these kind of abstract things where you're like, how do I turn that into a risk? How do I turn that into like a numerical value that I can punch into this thing? I know the
Yeah.
code works. I know this thing works over here, but I need to put something in. And that's something that I always spend a lot of time like going, this is a leap of faith here, before I start doing stuff.
I mean, this is one of the big reasons I think all these kind of slightly over enthusiastic projections about what technology will do to us and our professions and so forth. I think this is where, if they get it wrong, this might be one reason why they get it wrong, i.e., this is hugely dependent on the engineer's knowledge and intuition and expertise and their sort of understanding of everything else that's going on within the system that they're designing, and be able to take all of that and then distill it into something that you can simulate in a model. Because once you've created the model, then the mathematicians can come along and they can solve it. And that's, yes, it is challenging, and yes, it is very interesting, but that's, in a way we know how to do it, right? But it's actually the idealization and understanding what to model and when to model and what values to assign to things. That is more of an art rather than
Yeah.
it's interesting. I this house I'm in, we moved in, and it was like the only house we could afford was a tatty house, and it needed a lot of work doing. So as we moved in, we got some work done, and we kind of knocked on a wall and extended some beams to sort of span the entire space. And to kind of, I knew how to design those beams because I've done this in undergrad, right? I know exactly what I've written the software to design these beams, right?
Yeah.
But what I don't know is, what is the reasonable amount of loading that ought to come on this? And, and I had to go to one of my kind of colleagues to consult on it, to sort of understand that what I was doing was grounded in reality. And the funny thing was, when I gave that to the builder kind of, they had to combine two beams to make it like a single beam. So because it was kind of spanning
Like they had to,
twice
they
the
had to splice the beams.
just well, we knocked on a wall, and then the beams were ending at the wall, so basically supported on the wall, and therefore they had two beams basically hanging in midair. So they could either connect these beams, or they could replace it with another beam. But actually, what you've done is you've doubled the span. But if you just connect the beam, which is what he was trying to do, then you would, is a deflection, does it grow by the fourth power or whatever? So that beam would have been inadequate. So I actually knocked up a quick simulation model to show him how the beam he was actually proposing to put in place would actually collapse. And the expression on his face was priceless, right? When he, um,
Yeah.
yeah,
That's good. That's good stuff. I can only imagine for any contractors that are doing work within the home of a structural engineer, it must be it must be a nightmare. Coming showing him a numerical analysis for a beam in your living room.
yeah,
Um,
yeah, I
so
know that. Mm.
I guess we're running low on time here. Your thoughts on you mentioned a few ideas which I really liked, but your thoughts on the future of structural engineering. And what I worry about is as these different AI tools grow, we're just going to, place some of the responsibility or some of the thinking into those tools, which is obviously carries huge risk. But I think you nailed it in what you just said a moment ago, where there's always going to be this sort of like your professional voice of reason is really like the glue that's going to hold these kind of tools together. So, what do you see for the future of the industry? Like, what would you be telling undergraduates right now that are interested in this? With because it feels like the sands are shifting under our feet. Like, there's a lot of development right now.
I think the basics and yes, I agree with all of that. But I also think the basics and the fundamentals, they remain as important as they ever have been. And again, relating it back to some of what I've seen, or the kind of things that my team and I have been sort of building. A recurring theme has been, we are seeing these advancements in how engineers kind of work, and how they work with these tools, and how they work across various. It's not just one single tool in their toolkit, but across various interoperating between the various tools in their toolkit, being able to deliver designs more productively and so forth. A theme we've seen is quite often there's a risk that the practitioner loses sight of what it is that they are analyzing or designing, or sort of predicting.
Absolutely, absolutely.
Uh,
I've been guilty of that many different times during my career.
and it's a natural consequence of just an increase, sort of, there's a natural move towards becoming more productive, and therefore doing more with less time, and therefore less opportunity for us to have all the checks and bounds in place that we used to have. So there's two ways to counter that. There are only two ways I have seen so far. One is having these strong fundamentals, having a solid base. I'd actually kind of argue for civil engineering education to be more mathematically oriented than it is today. And they
Really?
sort of,
So,
well, in the sense,
what's what do you think? While I agree with you, I think the problem is there's just so much material to cover, and
yeah,
it's difficult to decide what's the most relevant. And then in the actual profession, I have friends that I went to university with, and they have never done any sort of numerical design or computation work. So it's kind of it's such a broad field.
yeah. So I'm not necessarily arguing for more credits or more hours spent
Yeah.
learning more material, but actually,
Thank God, Ramaseshan.
yeah. But the way I mean it is, for people to have a bit more exposure to what happens under the hood when they learn these techniques, these numerical techniques, and more recently, the more machine learning type techniques. So again, that going back to the recurring theme, one thing we have been doing is, when people use these advanced tools, what are the meta tools do we need to give people the level of confidence that they probably need to have in their answers, uh, that when they lose that kind of, um, when they are in a position to lose that insight um, into the kind of, um, into the physics of what they're. So let me expand on that. I'm struggling for words. So if, for example, you're designing, let's say, a building that looks like a flat post, a cantilever, then you know what behavior to expect, vibration behavior to expect when you're designing for seismic, for example. But if you're designing quite a complex shape where you have a building sitting on top of a podium, and then another building or another tower sitting adjacent to that podium, and so forth, you lose a sense of intuition of what behavior to expect. And therefore, if you don't have that intuition, then how do you know what answers to expect, and how do you know if your answers are correct? And so one way to kind of tackle that is to give students a better feel for the underlying physics, underlying kind of, how these software programs simulate and predict, but also for these tools to then say, what other ways can we give you to check if your answers are correct, or whether you made any mistakes in your calculations. And so it's those kinds of, so I see that as a sort of, um, two sets of guardrails, if you will. One is, more solid fundamentals, but also evolving our tools to ask the question, what could possibly go wrong? Especially as you do machine learning, where when you're doing regression, you're putting numbers through a black box. You don't know how those predictions are arrived at. So one thing we've done is, for example, use the kinds of machine learning where you get confidence in your predictions and not just a single prediction. So yeah, it's going to be a set of techniques along those lines.
Yeah, yeah, and as you mentioned, I think statistics and the management of data and statistical techniques are going to become more and more commonplace, and they're going to be used more and more throughout the industry. So, Ramaseshan, thank you so much for discussing this stuff with me. You know, there are many things that I would like to go deeper down a rabbit hole with you on, and hopefully we'll do that in the future. Is there any messages that you have out there for people that are interested in your field of work? Like how can they get involved? It's quite a small niche.
Oh, that's a good question. Yes, I think the flip side to that question is we struggle also to find good people to work in these areas with the sort of right set of skills and attitudes, um, who can sort of who are ready to go on the journey of discovery. So I guess yeah, the off the top of my head, I think we try to kind of keep an open mind for where the field is heading,
Yeah.
and then try to build a set of specialism in you know in one of the subfields that might be of interest to someone. So that's the only sort of approach that I've seen work.
Yeah.
There might be other approaches.
Yeah.
Yeah, I think just on that note, I also wanted to ask you what your experience has been through Flowcode, because you are kind of, in some ways, there's an overlap here in terms of what you're trying to empower through Flowcode. I feel, i.e., getting people to discover these new ways of working, new techniques, and so forth. So, is that an accurate understanding of where you're headed, and what's your experience been with it?
Um, it's a good question. I personally I've worked in a lot of different sectors over my career engineering, and I've always found programming just interesting as a kind of a side thing.
Mm,
But maybe about 6 or 7 years ago, I started using more and more Python in my work. And initially, it was incredibly difficult because there was so much resistance,
mm,
because people didn't understand what I was doing and how can you check it, etc. So I just had to, double the level of effort to make sure that everything that I did was extremely transparent and legible for somebody to check it from first principles, which doubled the amount of work that I had to do initially. But then once I kind of validated how effective it was, people kind of relaxed a little bit and they were like, wow, this is really, really useful. And then it started with like a small subset of people that were interested in this because they saw the immediate benefits. And then I started talking to some friends about it, some people in the industry about how useful it was. And then it just kind of slowly morphed out from there. So, I mean, the whole premise of what I'm doing is just trying to show both practicing engineers out there and students who are interested in the field that these are all very achievable ways of working and doing things. And we can learn so much from other fields, and just incorporate them into what we're doing. And that's why I'm so interested in what you're doing and how your use of statistics and data informs, you know, business decisions. And
mm,
I think that's so important. So I don't know. I this flow code thing has been fascinating for me. I get to meet people like you. I get to have interesting conversations like this, and to me, it's like nourishment for the mind. I really enjoy it. And you've said a bunch of things today that have sparked ideas in my own mind that I've been sketching down, and I'm going to explore those myself. Down the line. That's the great thing about our industry, is that, like, every time you learn something, it's like you're scooping up a little bucket from an ocean, and you're just standing there holding your bucket going, wow, look at me, look at this bucket. but you're looking out at the ocean.
Yeah, and I also find people are quite happy to have these conversations and share. And so I've learned similarly from a lot of these. In fact, your own podcast, to be honest, your previous guests. So yeah, cool. So yeah, thanks for having me.
Of course, Ramaseshan, thank you very much. And for anybody out there with questions, comments, always let us have it in the comment section. Don't hold back. We can take it. And be good out there. And I'll see you guys in the next one.
Yeah.